Hi there. In today's lecture, I'd like to introduce some of the concepts of Einstein solids and show you how to find the multiplicity for an Einstein solid. So first of all, you need to understand that Einstein solids are how we model solid materials. They're a common model anyway that's used in thermodynamics for modeling solid materials. So what is it? Well, what we're doing is we're modeling a solid as atoms arranged in a lattice, right? And each atom sits within its lattice position, and it's free to vibrate a little within that position, but it doesn't hop around. Now, we're going to model the atoms in a solid as balls, and the bonds in between the atoms as little springs, as you can see here in this little cartoon. Now, the only thing is, these springs are quantum harmonic oscillators and not classical oscillators. So I thought it might be nice to review some of the things that we know about classical and quantum harmonic oscillators so that we're all on the same page with the notation and everything. So first of all, a classical oscillator is governed by Hooke's law, okay? So Hooke's law says that if you have, for example, a mass and a spring like the one shown here, if you displace that mass from the equilibrium position, which means moving the spring mass system away from the place where it just likes to hang or sit naturally, then that means that you've pulled or pushed it away from its equilibrium position and the spring has then been extended or compressed. Now Hooke's law says that the force from the spring wants to return the system back to its equilibrium position. And so there'll be a force that opposes the displacement. That's why the minus sign is there, right? Now the magnitude of this force is proportional to how stiff the spring is, which we call commonly a spring constant, K, right? The units of K are newtons per meter. And of course, if you had a stronger spring, K would be larger. And if you had a weaker, loosey-goosey spring, K would be smaller. X is the displacement of the spring from its equilibrium position. So the force is also proportional to how stretched or compressed the spring is. The further you elongate it, for example, the stronger the force that wants to return it to its equilibrium position. Now, if you solve Newton's second law, assuming that the spring force is the only force on that system, that's all there is, there's no damping or anything else going on, then you set Hooke's law minus kx equal to the mass times the acceleration. When you do that, you end up with a second-order differential equation. If you need more of a review on this, I have other lectures elsewhere. This is just a recap. So the acceleration is the second-order time derivative of the position, and then that becomes equal to negative k over m times x, where k is the spring constant, m is the mass, and x is the displacement for equilibrium. Now, when you solve this differential equation, what you end up with is a sinusoidal curve, okay? So the solution here is, for example, the position with respect to time is a, the amplitude of motion, times a sinusoidal function, here I chose cosine, cosine omega t plus phi. Now omega there is the angular frequency. So omega, from the previous slide, is equal to the square root of k over m. So how quickly the spring oscillates, how rapidly, at what frequency, depends upon the spring constant and the mass, okay? So phi is the phase constant. That's just an offset. Depends on where you start your clock, right? So if your clock starts at max displacement, then it's a cosine. If it starts at 0, you might have a sine, or it can start anywhere in between, and phi would be some arbitrary angle. Okay, so that's the solution to the classical harmonic oscillator. Now, the frequency of oscillation, which is 1 over the period of oscillation, right? F is equal to 1 over t, is equal to the angular frequency from that cosine function divided by 2 pi, okay? Remember that the frequency is the number of oscillations per second, and the period is the length of one full oscillation, right? How long it takes to go from, say, for example, the crest to the neighboring crest on the waves. The SI unit of frequency is the hertz. The SI unit of omega is radians per second, and of course the SI unit for the period is time, seconds. Now, if we assume that there's no other forces on the spring, right, just a spring force, no damping, no friction, then that tells us that the total energy of the system would be constant, okay? In other words, the spring would oscillate back and forth about the equilibrium position. When it's at its max displacement, right, when it turns around and goes the other way, the velocity is 0. So that means the kinetic energy is 0 at that point. But it's at its max displacement, and that would be the place for the largest potential energy. So what happens with no damping is that the spring oscillates back and forth, trading energy in between kinetic and potential, but always keeping the same total amount of energy, assuming no dissipative forces. Now, the kinetic energy equation from classical mechanics is 1/2 mv squared. If you solve for the velocity from that position versus time curve by taking the derivative, then you can see that 1/2 mv squared is equal to 1/2 m omega squared a squared sine squared omega t plus phi. That's what you get when you take the derivative, right? You're going to get the sine. Now, the potential energy for a spring is 1/2 kx squared. Okay, so U is equal to 1/2 kx squared. Now, if you plug in the equation for x of t into that, you end up with 1/2 m omega squared a squared cosine squared omega t plus phi. If you sum those two things together, the sine squared plus cosine squared goes to 1, and that gives you 1/2 m omega squared a squared. Now, solving, you can see that m omega squared is equal to k, and so that means that the total energy, k plus u, is always 1/2 k a squared, assuming no dissipation. Now, this shows us that we have these two parameters here, which are constantly trading energy, the kinetic energy and the potential energy. And what we'll see later in thermodynamics is that for every direction of oscillation, you get 2 degrees of freedom, one for the kinetic and one for the potential. Now, simple harmonic oscillators are really good models for a lot of physical phenomena, but one of the most important applications is the model of bonds as springs, which we see here. Now, the reason that we can do that is shown here in this little graph at right. If you plot the potential energy curve for a bond, it looks kind of like this orange curve here, okay? So this is the potential energy versus the separation between the two atoms. You can see that as R goes to 0, as the two atoms are squashed together, you get a hard wall repulsion, which makes sense, right? So your potential energy goes up a lot as it approaches R is equal to 0. There'll be a minimum to the curve, and then after that minimum, the potential energy will gradually increase. So it has kind of a long tail on the right-hand side and a hard wall on the left. But if you zoom in right down there close to where the minimum of the potential energy curve is, you can see that you can kind of fit that to a curve that looks like, you know, your 1/2 kr squared, right? So you can fit it to that curve right there, and that's why we can use the potential energy as modeled by 1/2 kx squared, 1/2 kr squared to fit bonds, okay? It looks kind of like it down there near the minimum, all right? So the potential energy acts similar to that of the simple harmonic oscillator, and this is why it's such an intuitive model. We've seen simple harmonic oscillators from almost day one in physics, right? And so it makes a nice model for people to understand what's going on with these bonds. Now, I said that the Einstein solid was a quantum harmonic oscillator, okay? So this is a model from quantum mechanics. You solve the Schrödinger equation, right, which is the quantum mechanical equation, right? You solve the Schrödinger equation using the potential energy for the harmonic oscillator, 1/2 kx squared. When you do that, what you end up with are energy levels that look like this one here in the diagram, okay? You have energy levels that are separated by the same amount in between levels, and that amount is h bar omega. More about that in just a second, right? And then even the n is equal to 0 state has just a little bit of energy, right? Because of the uncertainty principle from quantum mechanics, we have still just a little bit of energy down here in the ground state, or the lowest energy state. So the energy levels in a quantum harmonic oscillator go 1/2 h bar omega, 3/2 h bar omega, 5/2, and so on and so forth. Now remember that the main thing that distinguishes quantum from classical mechanics is that energies cannot be continuous for systems. Instead, they're discretized. Okay? The reason that we don't see this discretization when we're dealing in the macro world is because the separations are so tiny that they're not really visible. But if you start to look at certain phenomena, they pop right out, okay, like the energy levels, for example, in a solid. Okay. Now, I said that the energy levels were separated by h bar omega, and that the energy levels went 1/2, 3/2, 5/2, etc. times h bar omega. So just to remind you, h is Planck's constant, which is one of the fundamental constants of nature, right, from quantum mechanics. It's 6.626 times 10 to the minus 34 joules seconds, okay, in SI units. Now, in a lot of quantum mechanics equations, h is divided by 2 pi, and that's h bar. So h bar is equal to 1.055 times 10 to the minus 34 joules seconds. Okay? Now, h bar times omega is equal to hf, right? Because remember that omega is equal to 2 pi f. So that means that the energy levels in a quantum harmonic oscillator are going to be proportional to Planck's constant times the frequency of the oscillation. All right? Okay, so let's come back to this now that we've had our little review and talk about what's going on with Einstein solids and find their multiplicity function. So Einstein devised this model of a solid material in 1907. What he was trying to do was to describe the heat capacity of solids, and he did that successfully. And then his theories supplanted the rule of Dulong and Petit, which was a classical approach, mostly, to heat capacities. Okay? We'll talk more about that later. So an Einstein solid, we're going to use the terminology here, is a collection of capital N quantum oscillators. So those are the bonds. All of those bonds in our models are going to have the same stiffness. It is true that if you have a true solid material that you're going to have bonds between dissimilar atoms, right? So crystals are actually quite complex. If they have bonds between dissimilar atoms, they really would have different spring constants. But we're not going to get into all that right now. We're going to assume, say, a perfectly pure, beautiful metal like copper or something. And so all the bonds would have the same energies and hence the same spring constants in between them. Okay, so all the bonds are the same. Now, if you have N bonds, then that means since each bond, if you look in here at this atom here in the interior, it's bonded to its nearest neighbors, okay? And so if you have N bonds, then that means that you have about 1/3 as many atoms in general, okay? And you get that by dividing the number of directions that they're free to oscillate. So let's do a really simple look first at what's going on with how the energies here are divvied up amongst the different bonds, okay? And we're going to look first at the simplest possible thing that we can, which is maybe just one atom with 3 oscillators, okay? Let's say that we have an Einstein solid that has N oscillators, and we want to calculate the total energy of the system and how that energy is distributed amongst those atoms and bonds. So for this energy distribution function, we need to know what the multiplicity of the states are. So let's say that we have 3 oscillators as shown here in the columns in the table, oscillator 1, 2, and 3. Now, what we've got is I've broken them up into different amounts of energies, and I've given those different colors in the table. So the colors are black, red, and green as shown here. Okay? Now, black would be our ground state. That's the lowest possible amount of energy, which means that each of those oscillators is in the ground state on this energy level diagram right here. Okay, so each one of them is in the ground state. Okay, now if that's the case, then there's no excited states. What I'm going to enter into the table is the number of excited states that each atom is in. And so, for example, if I put in 1, then it would be sitting up here in the first excited state. If I put in 2, then it would jump up 2 states from the ground state. I hope that's clear. So lowest possibility, lowest amount of energy would be all of them in that ground state. So there's no excited states in each one. So that means that the lowest possible way to do it is 0, 0, 0 ground states for oscillator 1, oscillator 2, and oscillator 3 respectively. Now, what's the multiplicity of that? Well, there's only one way to do that, right? All of them have 0. There's only one way to do that. Okay. Now, let's go to the next lowest level. The next lowest level is if just one of those bonds is in an excited state, right? So if that's the case, there's 3 ways to do that, because that excited state could either be given to oscillator number 1, oscillator number 2, or oscillator number 3. And so the arrangement would be 0, 0, 1, 0, 1, 0, or 1, 0, 0. And those are indicated here in red for the next highest amount of energy. So that means the multiplicity for that would be 3. Okay? So the notation that I've used is for the ground state, omega of 0, that's my ground state, no excited states at all. That multiplicity is 1, so omega of 0 is 1. The multiplicity is 3 for having one excited state, so omega of 1 is equal to 3. Now, let's look at the next highest energy state, okay? Green is the category for that. That's if there's 2 excited states, okay? Now, how could we do that? Well, we could give one bond both of the excited states, right? That would be one way to do it. So that would mean that the excited state could be in oscillator 1, oscillator 2, or oscillator 3. And it could be 2, 2, 2. So it's arranged as 0, 0, 2, 0, 2, 0, or 2, 0, 0, right? That's one way. That's 3 ways to do it. The next is if 2 of the oscillators have an excited state and one of the oscillators doesn't have an excited state. Okay, so that's shown here in the bottom 3 rows of my table. In this way, the excited states are distributed amongst oscillators 1, 2, and 3 as 1, 1, 0, 1, 0, 1, or 0, 1, 1. Okay, so 2 excited states has a multiplicity of 6 because there's 6 possible ways that that can be done. So omega of 2 is equal to 6. Okay, so I'm not going to go any further with this. This is as far as I'll go right now, but I hope you get the gist of what I'm saying here. Okay? As you go up, as you have more and more excited states, the multiplicity will grow, right? So what's the function for the multiplicity that would describe this system, this scenario? So let's say that the number of oscillators is capital N, and the number of excited states that those oscillators have we'll call Q. If that's the case, then the multiplicity of an Einstein solid is shown by this function here. Q plus n factorial divided by Q factorial divided by n minus 1 factorial. Now, we use Schrodinger's thermal physics for our thermodynamics course, okay? The proof as laid out in that text I think is pretty intuitive for this function, okay? So what Schroeder says in that text is, okay, let's represent the excited states, the Q, as little dots. And then what we're going to do is we're going to put all the dots down for the total number of excited states that we have. And then we're going to put lines in between those dots to divvy them up, right, in terms of how many oscillators it's divvied up into. So if I have, say, for example, 4 oscillators, then I would need 3 lines to divide them, as shown here in this little cartoon down here. So to the left here, this dot, that is held by oscillator number 1. And then these 3 dots, see, in between these 2 lines are held by oscillator number 2. And then this dot right here is held by oscillator number 3, and then these 3 dots are held by oscillator number 4. So see, you divide them up with the lines. So it's divvied up. So that means that you need 1 fewer line than you have oscillators. Okay? So that's pretty clever, right? So that helps explain why it's n minus 1, okay, and not n in the description for the multiplicity. Okay? So this goes back to our combinatorial function. Okay? We have Q excited states, and we have n minus 1 lines, right, that divvy them up. And so then we have to choose how to arrange them, and that's Green's combinatorial function. Okay? So that's the proof, the derivation for that is sort of an intuitive one, as verbally described there. I do encourage you to read the text, though, for more information on that. Okay, now let's say that we don't just have one Einstein solid sitting there, because that's not very exciting, right? We want to describe thermodynamics, changing processes. So in order to have that happen, let's have two Einstein solids, and I'll call them A and B, and we're going to let those two solids interact with one another. So what we're going to do is we're going to place those two solids in thermal contact. Now let's say that we have a number of oscillators that's equal for A and B. We'll stick with 3 right now, okay? And object A is hot and B is cold. So we're going to represent hot as having a lot of excited states and cold as not having many excited states. That makes sense, right? So let's say that object A has 6 excited states and B is really cold and it has no excited states. So we're going to use our functions for the multiplicities and find the multiplicity for A and B separately. So that's q plus n minus 1 factorial divided by q factorial divided by n minus 1 factorial. So that would, for this particular scenario, with A having 6 excited states and 3 oscillators, be 8 factorial divided by 6 factorial divided by 2 factorial. When you do that, you get 28. So the multiplicity for the hot object is 28. Now, as we've already shown, the multiplicity for the cold object with no excited states and 3 oscillators would just be 1. But showing that here mathematically, right? Q is 0, n is 3. So then we have 0 plus 3 minus 1 factorial divided by 0 factorial divided by 3 minus 1 factorial. That gives us 2 factorial over 0 factorial divided by 2 factorial. 0 factorial is 1, in case you've forgotten that little thing. It is weird, though, I admit. So if we solve for that multiplicity, we get 1, okay? All right, so that's before they're placed in thermal contact. Now we place them in thermal contact, and eventually those two solids will come to thermal equilibrium because that's what happens. Now what that means is that now we can consider our independent systems, A and B, to be one big system. That one big system would have 3 plus 3 is 6 oscillators, but because energy is conserved, right, still has 6 excited states, okay? So now if we calculated our multiplicity, it would be 6 oscillators, 6 excited states, Q and N are both equal to 1. Plugging that into our formula for the multiplicity, we would have 6 plus 6 minus 1 factorial divided by 6 factorial divided by 5 factorial, right? So if we solve that equation, that's omega AB is 462. So we can already see that this multiplicity is a lot larger simply because there's more oscillators, right? Okay, now let's look at what's going on and how that energy might be distributed between A and B. Okay, now here's possible scenarios of what can happen. You place them in thermal contact, you let them to come to equilibrium. Well, the energy could theoretically stay in A, or it could be all transferred to B, or there could be an even split, right, between A and B, or some midpoint thereof, right? So, energy is conserved. We're still only going to have 6 excited states. So this table runs down how many excited states A might have and B might have. These are all the possibilities. Remember, we're not weighting these possibilities, right? We're going to consider all these to be equally likely. That's one of our fundamental assumptions in thermodynamics. So A has 0, B has 6. A has 1, B has 5. A has 2, B has 4. 3, 3, 4, 2, 5, 1, 6, 0. Those are all the possibilities of how it can be distributed. Now, let's go through that in the table, okay? A has 3 oscillators. If it has 0 excited states, the multiplicity is 1. A has 1 excited state, 3 oscillators. The multiplicity would be 3. And I keep going in the table. 3, 10, 4, 15, 5, 21, 6, 28. And these are all calculated from that formula. Omega is equal to q plus n minus 1 factorial divided by q factorial divided by n minus 1 factorial. But I'm just doing it for A. See here? I'm just doing it for A. Then I do it for B. Same thing. Well, B has 3 oscillators, and it could have 6 through 0 excited states. So the table kind of looks like the flip of A, right? They have to have 6 total, right? If A has none, then B has all of them. Okay, so that's how it goes. So now B's possibilities are 28, 21, 15, 10, 6, 3, and 1. So we're assuming these are all equally likely. So how does this shake out? Well, if you have the multiplicities from the previous table brought to this new table and placed in columns. If omega A is 1, B is 28, 3, 21, 6, 15, and so on and so forth. So how do you find the total multiplicity for the system A and B? Okay? Well, omega AB is actually going to be the multiplicity of A times the multiplicity of B. Okay? So when you're combining multiplicities from different systems, you're going to multiply them. All right? So 1 times 28 is 28. 3 times 21 is 63. 6 times 15 is 90, and so on and so forth. Okay? Going down the table here, you can see that the highest multiplicity for the combined system AB is going to be 100, right? All the others are smaller than that. Now, that highest multiplicity is for the result where A and B have equal amounts of multiplicity, 10 and 10. That means that each of them have the same number of excited states. Okay? So, if you then compare the multiplicity of system AB for these different scenarios with the total number of possible outcomes, right, which we already showed would be 6 oscillators, 6 excited states, giving a total multiplicity of 462, then we could calculate the probability for each one of these ways that the energy is distributed, right, by taking that omega AB multiplicity and dividing it by the total multiplicity, which is 462. This means that you've got probabilities up 6%, 14%, 19%, 22%, and then going back down, right? So the highest probability state is the one where the excited states are equally shared in between oscillators A and B. Okay? So, my punchline is, you can see that the most probable state is the one where A and B have equal numbers of excited states. Now, this is just a simple example, the simplest possible example that we can get, right? I mean, it's very easy and straightforward. 3 oscillators per system, right? 6 total excited states. Those probabilities are only going to get even more extreme and skewed toward equal sharing as the system gets larger. So Schrodinger's text actually takes you through a system that has 500 oscillators and 100 excited states. Now that's not even approaching a real world system, but the effects are even more dramatic, and the probability for equal sharing in between the excited states is even larger for the even, right? Now back up a little bit more and take that result and think about the fact that a macro scale object is going to have something like, 10 to the 26 oscillators. Okay? Wow, it's a big deal. And when you get to real world size systems, eventually you can see that it ends up that you would have to wait longer than the age of the universe to see a system where energy would spontaneously flow from a cold object to a hot object. It just doesn't happen. Now, this isn't for some fundamental reason. It's just probability. It's just statistics. That's why the second law of thermodynamics works, right? It's not because you've got some inherent thing going on. It's just that is the most likely thing to happen. That is the system with the largest amount of disorder. The excited states going everywhere, right? Being evenly distributed. That's very disordered compared to an ordered system where one of them keeps all of the excited states and it doesn't move to the other, right? So that's why the second law of thermodynamics works. Sheer probability. Okay. Well, with that I'm going to stop. I hope you understood that and liked it. Let me know if you have any questions in class, and as always, I'll see you then.